Thank you so much. Thank you for coming out tonight. I'm talking about the universe in a box tonight, which is really a book about discovering our cosmos. And it's a story, but it's probably not the story that most people know about how we found out about this amazing universe that we live in. Because it puts computers at the center. And the way that computers and their steadily increasing power over the last few decades have taught us totally new things about the cosmos, about space, about what's in it, and about how we should even really think about it, about what's actually going on around us. And more than that, it's a story about cooperation between many different people working on very, very different topics at different times, even in completely different fields of study. And the way that all of those ideas from these different people have really been brought together on a single canvas, a digital canvas that's provided to us by computers that enable us to understand more deeply what's going on in our universe. And I want to give you a taste of that tonight. I want to show you some of the discoveries that we've made about the universe using computers. But I suppose to get started, we first need to just have a look at the real universe, the universe as it actually is out there, as seen through telescopes. And I'll give you a hint that, towards the end of today, I'll tackle a question that people have put forward, that maybe the real universe that we see out there is itself part of some higher simulation, a simulation being performed by some immensely powerful beings that are sort of beyond our direct grasp. But I want to park that for the moment and just look at the universe calmly as we actually see it. And if you look up into the night sky, if you do it from here, if you just go outside now and look up, you don't see that much, right? You see a few stars, you see a few planets, if you're lucky. But what you really need to do if you want to understand the universe that we live in is pause and allow your eyes to adjust so that they can adjust to the dark conditions. In fact, even better if you can get outside London, as far away from city lights as possible. And if you do that, then your eyes adjust, and first of all, you'll see a few hundred, and then maybe a few thousand, if it's a really dark night, stars. And you'll see more than that. You won't just see the individual stars twinkling at you. You'll also see a sort of faint band of light splitting the night sky. And this is our Milky Way. It's actually not a sort of band of milky light as it appears to us. It's actually composed of hundreds of billions of individual stars. It's just that they're so numerous and so far away that they just kind of merge into this one band of light. And if you've never experienced that for yourself, I can thoroughly recommend it. I mean, it's really quite something to see that, and you don't need any equipment at all. You just need to get away from the city lights and take a look. But in terms of cosmology, in terms of the stuff that I do, in terms of the stuff that we are actually trying to put inside the box, inside the computer, this is really just the beginning. These hundreds of billions of worlds, and by the way, many of them may have their own planetary systems, rather like our own solar system. I mean, one of the amazing things that's happened in terms of telescopes looking at the real universe in recent years is the discovery of just more or less anywhere you look, pretty much any star that anyone studies, they find what's called an exoplanet around it. So there are all these worlds out there, and yet this is really just the beginning, because beyond our own Milky Way, there are other galaxies. So there's our Milky Way with its hundreds of billions of stars. If you know exactly where to look, then you can actually see with the naked eye the Andromeda galaxy, which is our sort of nearest neighbor big galaxy. It's a similar scale to the Milky Way. It's got hundreds of billions of stars as well, but it's far, far, far beyond our Milky Way. It's way out there in space, so it just appears to the eye as a sort of smudge of light in the sky. But if you have a good telescope, then it starts to look like this, and you can see from the outside what a galaxy looks like. It's a kind of swirling mass of gas and dust and stars. And of course, we can't tell directly, but we have no reason particularly to doubt that all of these stars also can have their own planets. There's no reason why those star systems would be any different from the ones in our own Milky Way. So that is something like 22 million kilometers away, and yet we're still on the cosmic doorstep. This is still not the scales of the universe at large, because the universe just doesn't just have sort of one or two of these galaxies. It's actually packed with galaxies. In fact, if you take a rough estimate, there are probably hundreds of billions of galaxies in the visible universe, each of those with their hundreds of billions of stars. This is an image taken by the James Webb Space Telescope that, if you've been watching the news in the last couple of years, you'll have heard a lot about it. This image is actually of a very tiny patch of the sky. It's around about, in terms of how big it appears on the sky, it's around about 1/10 of the diameter of the moon. So it's a similar scale to a picture that was taken by its predecessor, the Hubble Space Telescope. Something called the Hubble Ultra Deep Field was on a similar scale and revealed a similar story, that our universe is absolutely packed with dots of light. And each of these dots of light that you see on the screen right now, they are all galaxies beyond our own. And all of that is just packed into that tiny little bit of the sky. It's just that they're so distant that they're sort of, seen just as little dots in that area. And there's nothing special about that patch of the sky either. So if you wanted to know how many galaxies there are in the universe, you've got to somehow multiply this up by all of the patches of the sky that you could have observed over. And that's where you get these kind of estimates, and they are just estimates, of hundreds of billions of galaxies. And that's not all, because in a sense, the stuff that we're most interested in right now in astronomy and cosmology is not actually the stuff that's on the screen at all. Because what you're looking at, what this lecture theatre is made of, what the Earth is made of, what the Sun is made of, what the galaxy and all those other galaxies that are visible to us is made of, seems to comprise just about 5% of what's truly out there. And the remaining 95% of our universe is made up of materials that we actually don't even begin to understand. We do not know what they are. They are given the name dark matter and dark energy. Those are two different things. They behave in rather different ways, and they play very different roles. But we really have very little idea about what they truly are, about how they link to the things that we are made of and that we're familiar with. And so in a sense, a lot of what we're trying to do in astronomy and cosmology right now is to get to grips with that. What is this 95% additional material? We don't see it directly. It's called dark matter and dark energy, but in a sense, it's not even really dark. It doesn't create shadows or anything like that. It's more like transparent. It just doesn't seem to interact with light in any particular, in any way. And as a result, you can't see it directly. We only have indirect evidence that 95% of the universe is out there. But the indirect evidence is actually extremely strong. It's extremely strong partly because some of it is really compelling, and partly because there is lots of it coming from different angles. There are many different lines of evidence that are pointing in this direction. So one of those is an effect called gravitational lensing. This is another picture from the James Webb Space Telescope, now looking at a different part of the sky. And what you might notice if you look at this is that a lot of the galaxies that you see seem to be sort of distorted into a kind of ring-like feature at the center of the image. And what's going on there is not actually that those individual galaxies have taken on that weird circular shape. actually what's going on there is that the light from those galaxies is traveling long distances through the universe. And as it does so, it's being deflected by gravity. So our universe has got an awful lot of stuff in it. The stuff generates gravity, and the gravity can do all sorts of things. It can pull material around, but it can also pull light around. So as light goes through the universe, if it happens to come across a particularly dense patch of our universe where gravity is particularly strong, its path through the universe gets bent. And that leaves you with these very particular distortions in the images of the galaxies that we actually see when we pick them up with a telescope like the James Webb Space Telescope. Now, if you ask how much gravity is required to enable that level of distortion, then you can do a calculation. You can find out what is the strength of gravity that enables this kind of distortion. You can then go a step further and say, how much material do you need to generate that gravity? Because gravity is something that is generated by mass. So the fact that gravity is pulling us down to the Earth's surface is just reflecting that the Earth is very massive. So to make something like this happen, you have to have an awful lot of mass. And it has to be in just the right places as well. And so gravitational lensing allows us to infer what's out there, even if the thing that we are looking for is itself transparent, because of its effect of distorting the other galaxies. And this is one of the lines of evidence that leads us to understand that there's much more out there in the universe than what we see directly. You cannot account for this level of distortion if you just assume that the gravity is being generated by the stars and the gas and the things that you can see directly. So the universe is full of these sort of additional materials that we are still really only just starting to understand. But actually, to come back to simulations, one of the strongest pieces of evidence we have that this is correct, and I told you, the thing that makes it compelling is the fact there are so many lines of evidence that tell us the universe has this extra stuff in it. And one of the most compelling is when we look back in time and we try to make sense of the history of our universe. This is something that simulations have proved incredibly valuable for doing. So we're lucky in a sense that light, although it travels really fast, it still travels at a finite speed. So still in the real universe, if you look to large distances, you are in a sense looking back in time. When you get light from the sun, it's taken several minutes to reach us. Or if you wait for light from Andromeda, it could take millions of years to reach us. So if you look far enough in our universe, you're looking so far back in time that you can see the universe as it was when it was actually very young, about 400,000 years old, which doesn't sound particularly young, but compared to the age of the universe, which is 13.8 billion years, 400,000 years old was really the baby universe. And again, this is a real picture, albeit in false color. So this is a false color representation of a sort of real image of the baby universe taken by something called the Planck satellite, specially designed to tune into that really, really ancient light that tells us about what was going on right at the universe's start. Now, what you'll see there is it looks sort of a bit unimpressive. It's sort of just ripples. It doesn't look like very much. But that's kind of the point, that the universe back then was a very, very different place. It was not a place full of stars and planets and galaxies and things that we can identify and look at as individual objects. It was actually more just like a kind of desert with some little ripples on it. So it's just sort of little ripples going through the sand, more or less just a flat, plain desert, very boring, very featureless, with tiny little ripples going through it. And it's those ripples that have been picked out here in the false color. So the question then becomes, how is it that a universe can start out like that, featureless, without any objects of any interest particularly, and end up as we see it today, 13.8 billion years later? And the answer, once again, is gravity. Gravity is a sort of universal force that acts across our whole universe, and it means that even if one part of the universe starts out with just a tiny bit more stuff than its neighbors, then it generates just a tiny bit more gravity than its neighbors. That means gravity is now trying to suck material into that little area that just started out just ever so slightly denser than its surroundings. So gravity has this property of being able to draw things together. And if you wait for 13.8 billion years, that can be quite dramatic. So in fact, the loose idea is that you start from something like on the left, and where your ripple just has gathered a little bit more material together, just a few more sand grains, over time, gravity pulls in all the surrounding sand grains, and it starts building interesting things like galaxies. There's just one problem, which is that this process could not possibly get you from the left-hand side of this to the right-hand side of this in 13.8 billion years. It wouldn't be fast enough unless you've got something providing a kind of additional tug. And once again, this is where dark matter enters the picture. It's the idea that you have some additional stuff out there that can create extra heft and accelerate this process of building interesting structures. So how did we learn all of this? Well, it's from very expensive telescopes that help us to actually look at the real universe. But in terms of understanding what's feasible, can you get from the left picture of the universe to the right picture of the universe in 13.8 billion years? The actual equipment you need to figure that out is more like this. This is something very close to my heart. I actually spent the early years of my life tapping away at these little rubber keys, playing around with learning how to program and things like that. And I've probably just given myself away as the world's biggest nerd, but that is literally what I was doing for most of my teenage years. It just seemed amazing. You know, you can create your own worlds inside these machines because they accept instructions. You can tell them what you want them to do, and they do it, which is a kind of mind-blowing when you're young. It's still mind-blowing now. And I think, you know, I was under the impression that this was a totally new idea at the time, and it was sort of the new frontier. Of course, it's not. You can go back in time, and the idea of computing things about the universe is extremely old. This is the Antikythera mechanism that was discovered in a shipwreck off the coast of Greece in the early part of the 20th century, I think it was discovered. It's a very sort of intricate set of meshing bronze gears that is believed to have been made around 50 BCE. And it shows that people were trying to do very sophisticated astronomical calculations using mechanical computers all the way back 2,000 years ago. So the idea of trying to sort of compute the universe is by no means new. But there is a big difference between what I was doing on the ZX spectrum and what's possible with something like this. You know, this is a fixed set of meshing cogs, and it could do very sophisticated calculations to do with orbits of planets and predictions of eclipses and things like this. But what it couldn't do is kind of step outside what it was pre-programmed to do. So you couldn't take something like this mechanism and calculate something completely new on it, like calculate something to do with, I don't know, the way that two stars can orbit around each other in the distant universe. Because you would just have to completely redesign the gears from scratch. The gears are particularly designed to do one thing. So the thing that has made computers uniquely powerful in our quest to understand the universe is the fact that actually, today, they're very flexible. And the idea for a sort of flexible computing machine can be traced back at least to the 19th century, the work of Charles Babbage and Ada Lovelace in envisioning a machine. In their case, it would have been driven by steam. It would have done its calculation by turning giant cogs and big metal bars and so on. But the core idea of it being customizable, that you could tell it what to do you wouldn't have to sort of change any of the gears or anything to give it a different instruction. All you would have to do is give it different instructions coded on bits of paper, actually. You'd punch holes in bits of paper and provide instructions to it that way without ever changing the machine itself. So you could change your mind about what you wanted to calculate without having to re-engineer the computer itself. So that was a breakthrough. Unfortunately, the thing never actually got built in full. This is just a portion of it. And, the accounts slightly differ about why it was never built in full, but probably a large contributing factor is that Charles Babbage was really not a particularly nice person by most accounts. He was just kind of grumpy and fired all the engineers who were actually working on it because he decided they weren't good enough. And then he resigned from his professorship in Cambridge because he decided Cambridge wasn't good enough. And then he fell out with the Prime Minister because he decided the government wasn't good enough. And basically, he was just really, really hard to work with. For some reason, famous Ada Lovelace still managed to work with him, despite all of this. And in fact, she wrote down a lot of what we now consider to be the kind of most foundational insights about what computers are good for, why they're so exciting. And for us, who are trying to understand the universe, one of the insights that she wrote down was that you could actually use this machine as a kind of prediction engine to predict what you might expect to happen in any given circumstance, starting from laws of physics. And she wrote, that if you were to make this machine, then you could look at physics as not merely a vast body of abstract and immutable truths. I mean, personally, I think a vast body of abstract and immutable truths is pretty good, but it's not merely that any longer. You can actually put it to some kind of practical use, and you can start doing calculations that are actually useful. And in fact, one of the first tangible ways that computers were put to use in conjunction with physics was in trying to predict the weather. So predicting the weather is an incredibly practical thing to be able to do. We sort of take it for granted today, but we shouldn't do, because it's not just a convenience. Literally it saves lives. If you know that there's a storm coming and you can get out of its way, then computing the weather actually saves lives. It's about as practical as you can imagine. And perhaps a bit more surprisingly than that, predicting the weather has a lot in common with understanding the universe. So I want to sort of draw that out a bit, and as I do in the book, I want to draw out that parallel. So to start with, you have the idea that physics can be encoded in what we call differential equations. Differential equations are a special type of equation that tell you how things change over time. And that's what physics is all about. It's how things change over time. If I throw something up, then after a certain amount of time, it'll fall back down again to the ground. Those are the kind of predictions that physics is concerned with. What physics isn't really able to do is tell you a starting point. So this is kind of obvious in the case of the weather. If you want to know whether it's going to rain tomorrow, for example, then you're not going to really do very well just looking at the laws of physics in abstract, even if you have access to the world's biggest supercomputers. On their own, the laws of physics won't help you. What you also need to know is the state of the weather today, because the state of the weather today is what's going to determine the state of the weather tomorrow. If you're worried about a storm coming, you need to know, where is it today? What's it doing? What's its track? And more generally, this is known as the problem of initial conditions. Initial conditions are not something that typically you can compute from physics. There is no law of physics that will tell you what the weather is doing today unless you know about the weather yesterday. And so actually, in terms of moving towards a world in which physics could be computed, in which useful predictions could be made, both about weather and about our universe and about other things, one of the most important steps was in getting to grips with the problem of initial conditions. And so in terms of the weather, it wasn't really possible to do good weather forecasts until you were able to gather together a picture, a snapshot of what the weather was up to today. And that was made possible by the invention of the telegraph system. And there was an exhibit, one of the sort of star exhibits of the Smithsonian Museum in Washington, D.C., was a kind of map of the US where they would get remote observation stations, weather stations would telegraph in the state of the weather today. And then the curator, Joseph Henry, would kind of gather all of the information together and make a map, much like a weather map that would be familiar to us today, just to show what's going on right now in the weather across the US. And then, from there, it's a sort of small step to go, well, now we can start making predictions about what will happen next. But you've got to take that first step. You've got to know what the initial conditions are like. And to kind of give away what's really important to us in cosmology, we have a problem with initial conditions. You know, what do we mean when we talk about initial conditions for our universe? It's one thing to say, you know, for a weather forecast, we know what the weather was like yesterday, that's fine. But if we really want to talk about initial conditions for the universe, then we have to somehow know what was going on in its opening moments, you know, in what we sometimes call the Big Bang. And that's extremely hard. Almost by definition, physics doesn't really give us an answer to exactly what was going on then. So we have to rely on a combination of different ideas, partly based on observing the real universe. But I'm going to come back to that in a moment. I just want to park the idea that initial conditions are really important if you want to use a computer to make any kind of predictions for the future at all. So the fact that you can take those initial conditions and combine them with physics, or in mathematical terms, differential equations, and come up with a prediction is itself not at all obvious. You know, you could imagine writing down a bunch of equations that are supposed to tell you how things change over time. You plug in what you think the early state of the universe or yesterday's weather was like, plug all of this in, and then you just sort of get meaningless rubbish out. You could imagine that happening if the equations weren't sufficiently well behaved. But luckily, we have something called the Cauchy-Kovalevskaya theorem, which tells you that if you have good enough equations and good enough initial conditions, then it is possible to make some kind of predictions. This is a theorem in mathematics that tells you that the kind of thing that Ada Lovelace was talking about making practical predictions of how things change over time, is within reach, at least in principle. So all of these ideas were kind of there in the background, but at this point in time, of course, there were no computers available. So it really wasn't possible to make any kind of forecast for the weather that was based on really proper physics. You could look at the weather maps and take a guess, but actually doing the calculation seemed beyond reach. Except there was a very singular figure called Lewis Fry Richardson. He's a kind of absolutely extraordinary guy. The more you read about him, the stranger he seems. And he just asked himself, why not? You know, if it's possible in principle to be able to predict tomorrow's weather starting from the observations today, using the laws of physics, then why not? Why don't we go ahead and try and do it? Now, as you can imagine, actually doing the calculations that enable this is nightmarish. I mean, it really is. I mean, this is an extract from his book, a sort of table of numbers, but there were sort of, you know, dozens of these. You would start with a sort of tabulated set of information about the weather today. Then you would follow through a whole bunch of calculations. Almost looks like a sort of doing a really complicated spreadsheet, but of course doing it all by hand. And to cap it all off, he was actually doing this on the World War I front line. It was a pretty extraordinary thing to apply himself to. Now, there is no way that even the most talented mathematician could calculate fast enough to predict the weather ahead of time. In fact, it took him weeks and weeks of calculation to predict the weather going forward by just a few hours. And so, in a sense, he wasn't really aiming to do anything practical. He was more trying to prove the point that it does work in principle. And when it came to figuring out, well, then, okay, if it works in principle, how do you actually make it work in practice? There, he didn't seem to be familiar with the ideas about, computers. And so he came up with the idea of a giant amphitheater, a bit like this one, where you just have loads and loads and loads of people all doing lots and lots of calculations. And whenever anybody finished a calculation, they would have precise instructions for who to pass it to, and then the next person would take the result of that calculation and feed it forwards into the next calculation, and so on and so on and so on. He also made a sort of elevated pulpit for himself. This is in his imagination, by the way. Of course, none of this was ever built. But he made an elevated pulpit where, somebody would be almost like a conductor, conducting, telling people where to pass their messages, and so on. And so this is a picture that was drawn in the late 80s, trying to summarize what this might have looked like. And you can actually zoom in and you can see the individual people doing their individual sums. And it's a beautiful vision. And he actually was kind of, it's hard to tell how serious he was. He wrote about this at length in his book. And also went on to describe that outside the amphitheater there would be nice fields and things because people would get tired and they need to go out and have a bit of a run around and breathe fresh air. And he was a strange guy, but he clearly, he was on to something. He was on to the right kind of idea. He just had the wrong way to solve it at the technical level. And who could blame him? He was doing this in the early part of the 20th century. Don't forget that, of course, the work of Charles Babbage and Ada Lovelace had never actually produced any machine that could do any calculations, so it just wasn't possible. But actually, computers at this point weren't that far off. So the so-called ENIAC machine, which was built in large part during World War II, in large part to aid the nuclear weapons development program, the ENIAC, one of its first sort of ostensibly non-military uses was to start doing weather forecasts. So taking all of these ideas, but now putting them on a digital computer. So this is now sort of following a lot of the ideas we've been talking about, including the ideas from the analytic machine from Charles Babbage and so on, but now it's all done electronically. And suddenly, it makes it possible to actually do these calculations that we're talking about. And Jules Charny, who was a meteorologist, accompanied by a large team, made this work. And they actually started producing forecasts that could just about keep pace with the weather. So still wasn't quite practical, but it was getting there. And of course, ever since then, the rate at which computer technology has sped up and developed means that by now, the kind of forecasts they were making, you could do this on your smartphone in your pocket in milliseconds, the stuff that would take them a day or more. So the weather forecasters were essentially ahead of the game. Now, it's not actually it's not a complete coincidence that this military machine was used for weather forecasting purposes. There was an idea at the time that the next step in warfare was going to be fought over the weather, and that beyond nuclear bombs, the next kind of state-level control you could exert would be manipulating a country's weather. And von Neumann, who was instrumental in all of this, had the idea of setting people to work on predicting the weather on the basis that they would then see, if the military makes a certain intervention, if we explode a bomb here, what effect will that have on tomorrow's weather? Asking these kind of what-if type scenarios. What if we tried this? What will it do to the weather tomorrow? It's actually quite a terrifying thought. But luckily, it turned out that the results showed that actually it's extremely hard to manipulate the weather, extremely hard to do it intentionally in any case. Any kind of intervention you try to make in the weather tends to have very unpredictable effects. This is an effect known as chaos, that although some things are predictable, but interventions typically aren't very predictable in what they'll do to the weather. So that's good, but unfortunately, of course, what we have found is that these very same calculations that gave rise to weather forecasts also started predicting climate change and the mess that we now find ourselves in, and I'm going to come back to that in 1 second. So at this time, understanding the universe was sort of going along in parallel with these developments in weather forecasting. And there are many other figures that I could mention. I just picked out one. It's Eric Holmberg, who, maybe a little bit like Richardson, wanted to do this kind of idea of simulations, of predicting what will happen in different scenarios. But he didn't have access to a computer. And what he did is he had a laboratory where he set up lots of individual light bulbs, and the light bulbs were supposed to stand in for stars in a galaxy. And he set up actually 2 separate galaxies, so 2 sort of, if you could imagine, sort of 2 constellations of light. And in order to figure out how will those 2 galaxies affect each other, he used a light intensity meter to measure how much light is coming from different directions in different parts of his apparatus. And he realized that light could be used in a sense to stand in for gravity, where you have a sort of very intense light coming from over here. That corresponds, in a very mathematically neat way actually, the intense light coming from over here corresponds to a strong gravitational pull if they were real galaxies. So he was able to do some very, what would have been very involved calculations, but making use of light to kind of do the hard work for him and figure out how much gravity should be coming from different parts of these galaxies. And then he moved his light bulbs by hand. He figured out how gravity should be pulling them around and moved them around. And in that way, over time, his apparatus evolved. It changed from being 2 separate galaxies. The galaxies pulled themselves together and they coalesced in the middle and kind of flung out what we now call spiral arms of bulbs, sort of flung out as they kind of pass through one galaxy and fly out the other side. And that's what you can see at the bottom here. So he goes from his top configuration of 2 separate galaxies to the bottom one where they're merging. And this is absolutely a phenomenon that goes on in the real universe. This is a pair of galaxies known as, colloquially, as the mice. Galaxies really do merge, and they really do fling out these tidal tails. And although, again, he didn't have access to a digital computer, but he was doing the same thing that we're essentially doing with today's computers. He was using the sort of power of a machine to calculate what should happen next, taking steps through time, seeing how things change. But of course, he had to put in some initial conditions. He had to just by hand say, I'm just going to imagine that I have these 2 galaxies. I don't know whether this really happens in the real universe, but I'll just imagine that there are these 2 galaxies approaching each other and see what happens next. It's very, very similar to what we do today. And I wanted to mention one more kind of foundational work in how we think about computer simulations of our universe, which dates all the way back to the late 1960s, and was actually the first example, I think, of where a computer simulation just completely changed the way we thought about our universe. So this is Beatrice Tinsley. She was working at the time on understanding the brightness of galaxies. It seems quite esoteric. Brightness and colors of galaxies. Why are some galaxies slightly different brightnesses and slightly different colors? And she decided, because she had access to a computer, that she would try simulating this. And her particular simulations had to make a large number of assumptions. Very, very hard to simulate all the details of what's going on inside a galaxy. In fact, we still can't do that today. So she had to assume, again, some initial conditions. Okay, let's just assume that the galaxy starts off with a bunch of gas. And then she also had to assume some stuff about physics that at the time really wasn't known very well. things like how fast, if you have a box of gas, a big box of gas, how fast does it form stars? Because we know that over time, gas can collapse under gravity, get really dense, and when it gets really dense, it can light up nuclear fusion, and it generates new stars. How quickly does that happen? Well, Beatrice Tinsley didn't know, and we still don't know today, but you can have a guess. And what's really powerful about computer simulations that's still true today is that you can ask kind of what-if questions, and that's what she was doing. She was saying, let's just try out different things. Let's imagine that we have this much gas and it turns into stars at this rate and it generates this many heavy elements. Then what will happen next? And what this kind of experiment inside the computer convinced her was that the assumptions people were making about the lives of galaxies were all wrong. And that really mattered because people were trying to map out galaxies across the universe. They were trying to use that to figure out how is the universe expanding, because we do know our universe is expanding over time. That's definitely true. But at the time, there was a consensus that that expansion was going to end in a few billion years, and then the universe would recollapse in on itself in what was sometimes called the Big Crunch, and that the universe would end after 7 or 8 billion years or so. That had an expiry date on it. And what Beatrice Tinsley's simulations showed is that that's making very strong assumptions about what you're seeing in the real universe. It was in particular assuming that one galaxy was much like any other galaxy, that regardless of where you saw a galaxy, whether it was close to you or far away, at least on average, you could pretty much regard them as interchangeable. And what Beatrice Tinsley's work showed is that that was simply, it was untenable, because you couldn't make sense of the brightnesses and the colors of the galaxies while also assuming that intrinsically they were essentially very similar objects. It just didn't work, whatever she tried in her simulation. So even though there was no kind of, this wasn't kind of recreating the universe in a literal sense. It was just a bunch of numbers in a computer. But what the computer enabled her to do was to experiment and show that assumptions people were formerly making were just wrong. And that led to people realizing, actually, the universe doesn't seem like it's going to end, certainly not anytime soon. In fact, now, decades later, we don't think the universe has an expiry date. It appears to be not just expanding, but expanding at an accelerating rate. So it really doesn't seem like it's going to end, certainly not in that kind of big crunch scenario. So I have a final thing to say about weather and climate, which is the link between what we know and what we don't know. It's an incredibly powerful and important thing inside simulations. So this is Sakura Manabe. He won the Nobel Prize for his early work on simulating climate change. And essentially building on weather forecasting type models. It has a bunch of modules now. Now, these are getting to be much more sophisticated simulations. They've got modules inside them doing different things. Some of those modules are doing physics that we know and love. You know, physics that you can learn about in school or in university. Things like, you know, thermodynamics and the way that radiation moves through the atmosphere and so on. But rather like Beatrice Tinsley, there were other things that his machines were not powerful enough to capture, but that he knew mattered. So Beatrice Tinsley could not simulate a star forming, and similarly, Sakura Manabe could not simulate clouds forming in our atmosphere. Clouds are actually very, very small-scale features compared to the entirety of the Earth. So if you've got limited computer power, you have to really sort of simplify things down. And it is not possible to start from the laws of physics and learn about where clouds are going to form in the atmosphere. What you have to do is make some reasonable guesses about how clouds form, when they form, what they do once they've formed. And they're really important because they reflect a lot of light back out into space. So if you neglect clouds in a weather model or in a climate model, you're going to get it very wrong. So There are many other examples of this in weather forecasting. There are things that you cannot capture by the physics alone because it's just too detailed. The level of detail you would require, even today, is just way, way too fine, all the way down to, individual ice crystals forming in the atmosphere. If you really wanted just to use physics, you'd have to capture all of these things going on, and no computer is remotely powerful enough to do that. So you have to make some best guesses and see, are your results sensitive to what you're putting in for those assumptions? So let's get back to cosmology then. Here are the ingredients of a weather forecast. There are the initial conditions that I've spoken about, which they're the present-day observations. There's the physics, things like light, radiation, how does gas behave. And then there's what's called the subgrid, what I was just talking about, the stuff that you are never going to capture because you just do not have the computer power to do it. As it turns out, simulations of the universe work in much the same way. We have some extra bits of physics that we have to include. Gravitation is perhaps one of the most important ones, the way that gravity pulls different objects together. Our subgrid things, they're rather different. Things like stars, as Beatrice Tinsley was studying. Also today, black holes. We know that black holes have a really important role to play in sculpting our universe. Dust, believe it or not, actually matters. It's just kind of little grains of molecules that have stuck together in space. Cosmic rays, the list goes on and on. There are many, many things that are really hard to capture. But the big question is, okay, well, what do we do for our initial conditions? We don't have that ability that weather forecasters have. Now they have a very sophisticated network of satellites and weather stations. They can figure out exactly what's going on today and use it to predict tomorrow. What can we do in cosmology that's along those lines? Well, it comes back to what I showed you earlier on, the cosmic microwave background. So we don't know exactly what was going on in the opening parts, or the opening part of our universe, but we do have the ability to look back through time and see something of it. And we've been able to match up those observations with ideas in quantum theory that talk about what the universe might have been like in its opening fraction of a second. And essentially, it would have been a rippling mess. This comes down to something known as the uncertainty principle in quantum mechanics, which says that the universe, when it was born, can't have been completely the same from one place to another. The uncertainty principle forbids it. You cannot have things being precisely the same everywhere. There must be some level of uncertainty in how much material there is in different parts of the universe. Now, I'm oversimplifying here because this is not something I have time to go into today, but just to say that you can use this idea to make calculations. You can verify those calculations against what we've seen of the early universe through the Planck satellite. And then when you put this all together, we think we know roughly what the initial conditions for our computerized universe should be like. Now, there are lots of buts there, and you can dive into the detail of that, but we have some idea of what the early universe was like. So we can now bring all of this together. We can bring together the ideas around physics encoded as differential equations and the fact that with our initial conditions that we've just made, we should be able to make predictions. We can add in those subgrid rules that are just saying we don't have the computer power to get everything right, so we've got to make some reasonable guesses about things like how stars form and how black holes behave. We can put it all together and we can produce a computer simulation. Now, we're not doing these anymore on ZX spectrums, as you can imagine. We're doing these on some of the world's biggest supercomputers. This is actually a movie I made 10 years ago, and it stood up pretty well despite the march of technology. And it shows a simulation from that time. Starting in the early universe, you see the universe is expanding. We've coded in the expansion of the universe into the computer code. And what you also saw is that in the early part of this video, everything looked fairly uniform. It just looked like a green blob expanding towards you. But as time goes on, as well as the overall expansion, you're starting to see that process whereby gravity pulls things together. So the very slightly more dense bit of the early universe starts to pull in all the material, and it makes this very distinctive pattern. I'm spinning around the universe so you can see the 3D structure. It's not really spinning. This is just for visualization. But you can see that it has this very distinctive 3D web-like structure. That is something that is very, very specific to dark matter. What you're actually seeing on here right now is not anything you could directly see through a telescope. It's dark matter. And of course, we have that freedom to tell our computer whatever we like. We can tell it to make an assumption that dark matter really exists and it behaves in such and such a way and there's so much of it. We can do those kind of what-if scenarios that I was talking about earlier on. What you can also do, of course, is switch views and take a look at what the universe would look like through an actual telescope. And what you now see is the same web-like structure, because all of this structure has been sculpted by the dark matter, pulling stuff around. But you can now see individual dots of light. And that's where individual galaxies are starting to form. We're only about 2 billion years into the history of this universe, so it's still fairly early on. Obviously, one of the nice things about doing a simulation is you can compress time into as short a period as you like and see how things play out. If I take a journey through this universe and kind of fly through, you can see that there are already these collections of many millions and billions of stars, and they're all kind of held in place by the gravitational might of the dark matter. We cannot get a universe structured in this way unless we have dark matter. This was one of the breakthroughs in the 1980s, in fact. The thing that really clinched the case that dark matter had to be out there was the fact that there is just no other way to get a structured universe like this. And make no mistake, when we look at the real universe, it really is structured in that way. The galaxies I was showing you earlier on, they're not just scattered at random. They're scattered along kind of very distinctive filaments of a web-like structure. So simulations in that way contributed to the growing evidence for dark matter in the 1980s and then on into the 90s. So I've restarted time now. What you'll find is that the simulation is showing that the dark matter is still there. It's no longer visible to you, but it's still there, making its presence felt, and it's pulling these galaxies together and helping them to merge. So this is much in the same way as in that laboratory experiment, throwing two galaxies at each other, seeing them merge and fling out these kind of spiral-like features. But now it's being done starting not from sort of assumption that two galaxies are going to collide, but from some well-motivated ideas about what was going on in the early universe, combined with those guesses about what the ingredients of the universe are. And if we go all the way forward to the present day, almost 14 billion years on, then all of these kind of little elements come together and they form lots of different galaxies. And here we're just flying into an individual galaxy. There is no way, by the way, any human spacecraft could ever do this. We've just flown, thousands of light years. You just flew. So, yes, that's right. Thousands of light years in the last few seconds. So there's no way that any human telescope is ever going to fly through our galaxy in that way. But we do have telescopes like the Gaia telescope that's trying to make a 3D map of our galaxy, just from a perspective relatively nearby to Earth, making a 3D view. And the fact is that actually these simulations do a pretty good job of recreating that view. It's not perfect. We never expected it to be perfect. There are too many compromises along the way. We've had to make guesses. We've had to make compromises in particular at that subgrid level that I was telling you about, where we have to be a bit creative about how we use the finite computer power to make a sort of almost infinite universe. But to a sort of first approximation, we're doing pretty well. And the name of the game now is to kind of refine that picture and figure out what are we getting right and what are we getting wrong? And there's a lot of, you see this sort of pop up in the media every now and again, but it's a long and difficult process to figure it out. And I think, what a lot of people are really aiming to do is to understand what is dark matter. We can put it into the simulations just by telling the computer there's this extra stuff, it doesn't interact except through gravity, it's there, please tell us what happens next. But what we'd really like to know is, what is it? And of course, we can do those kind of what-if type experiments. We can try putting in slightly different flavors of dark matter and seeing, does that affect the kind of galaxies that form? Does it bring it into better agreement or perhaps kick it into worse agreement with the real universe? And in that way, we hope to understand much more about what this sort of invisible mass of our universe is made out of. Another way you could do that is to build a giant collider, but you can choose. Do you want a giant collider or a ZX spectrum? I mean, if you're on a budget, I can recommend the latter. So this is the way that we are trying to uncover what's really going on. But before I finished, I wanted to say something about the real universe again. Because all of this progress, all of this ability to create digital worlds that seem so convincing, both in cosmology and simulations and also in the arena of computer games and so on, we seem to be creating realities that are more and more and more like the real thing. And of course, that kind of leads you to question, well, when we look out at our universe, is that real? Or is it some kind of digital mimic itself? Is it possible to imagine that the universe itself was actually created inside somebody else's computer? And pretty serious people have raised this as a possibility. Well, okay, some not so serious people, but so Elon Musk's take on it is that games are becoming indistinguishable from reality. And that then, if you think about all the possible computers that could be built and all the possible computer games that could be made, then the odds are that you're in one of those and you're not actually in the kind of base reality, the real reality at all. But if you're not impressed with Elon Musk, there are other more serious people who take this view. Richard Dawkins has written that he concludes we could very probably be part of a simulation by future humans, inside some future cosmologist's computer code. So, I mean, it sounds crazy, but serious people sort of take it seriously. And so I got to worrying a bit about this. And it is true that, as we were saying earlier on, the remarkable thing about physics is that it's computable. You can make predictions. Therefore, you can kind of mimic reality inside a box, inside a computer. So maybe it's not crazy. And in fact, the philosopher Nick Bostrom, who certainly is a serious person, wrote a paper kind of arguing from a philosophical standpoint that this is actually extremely likely because of all of the future simulations that are going to be performed. And again, it's that sort of counting argument. So many of those future simulations, and yet just one reality. So maybe we're already inside the simulation. So I want to tell you why I don't believe that that's actually true. So if you look at our very best computer simulations today, they're composed of about 10 to the 14 bits. So it's one with 14 zeros after it, bits. And a bit is a unit of digital storage. It's a sort of irreducible unit of computation, if you like. And you can look out at the universe and take it at face value and figure out, okay, well, how many bits would you have to recreate the whole universe without any of the approximations I've been talking about or the assumptions that I've been talking about? And the answer is 10 to the 124 bits. And not just that, but they can't just be normal bits, they've got to be qubits, which it just means that they're bits inside a quantum computer rather than bits inside computers that we actually have today, which are classical computers. So that's a giant leap, and some would say, don't be afraid to make giant leaps. But I would say it's so giant that when we start claiming to reason about simulations that people might be running, if they had that kind of power available to them, I mean, they would need literally every last scrap of material in the universe to build this computer, apart from anything else. So that when we then start reasoning about what they're up to, I think we're on very, very shaky ground indeed. And at some level, of course, it's just a curiosity and not something that really matters. People can make these arguments if they wish to. But on the other hand, I think there is a sort of serious aspect to it, which is that we live at a time when science, and indeed our very notions of truth and reality, are constantly being called into question. It's a really horrifying trend, the way that we're basically all being gaslit all the time about what's really going on around us. And I think when we as scientists start stepping into that and start telling you, oh, look, maybe the reality that we live in is not in fact real at all, then we're treading a very dangerous path. And so I think extraordinary claims require extraordinary evidence, and short of that, I certainly don't believe that we live in a simulation. But I do believe we should all know more about simulations, and luckily, if you want to know more, there is a very fine book. Thank you very much.